Hello everyone, today we're going to talk about how to do basic proofs problems. Proofs problems can be tricky at first because they are probably more open-ended than what you're used to dealing with. Thankfully, there are some common tips, tools, and techniques which you can use to make the whole process a bit easier. First off, for any proofs problem you'll ever encounter, there are always three key steps you have to do in order to do the problem correctly. Number one, you have to make sure you understand all of the definitions that appear in the statement you're trying to prove. And you have to make sure that you understand each definition word for word. It's very easy to end up in a situation where you feel like you understand what a concept means, but the definition in your head doesn't actually line up with the definition that's given to you. Also, I know that sometimes when you're learning a new definition, like three new definitions can appear within that definition, so you end up going down this rabbit hole of learning definitions and learning the definitions in those definitions and so on. There's no way to avoid this. You just have to power through and trust that the chain of definitions will stop at some point. In addition to knowing the definitions, sometimes you also have to make sure that you know all of the related theory. For example, if you're in linear algebra and you're trying to prove something about determinants, you should make sure that not only do you understand what vectors and matrices are, that you also know all of the basic properties and theorems surrounding vectors and matrices. Step 2. Before you prove a statement, you first need to figure out why that statement is true. Before you can make an argument that convinces other people, you first have to make an argument that convinces yourself. And to do this is not easy. In fact, it's the hardest step of the whole process. You have to be really creative here. Try things out, try to solve some easier versions of the problem, make some deductions, and then after you've convinced yourself why the statement is true, comes step 3, where you have to write up your formal argument. I'm not going to go too into detail about step 3, because I think the best way to learn is through practice and also receiving constant feedback from someone you trust in writing proofs. However, I will talk about a few common mistakes people make when they try to write up their arguments formally. The two most common mistakes are having gaps in the flow of your argument and also not using clear enough language. You have to make sure that you don't jump to conclusions or skip important steps. Also, to make your argument flow better and be easier to read, you should use words that tie your sentences together like thus, hence, or because. Also, the shorter your proof is, the easier it will be to understand. And using math symbols or math terms when possible can shorten large chunks of your argument. To make your formal proof look really professional, you'll want to type it up with software like LaTeX, which is free and easy to use. Okay, now let's take a look at some example problems. If P and Q are odd, show that P plus Q is even. So the first step is to understand all of the definitions. What does it mean for a number to be odd? A number is odd when you can write it of the form 2k plus 1, where k is an integer, and integers are just whole numbers with negative numbers, which we represent with this fancy z. Also, notice how when I'm writing out p and q, I'm using two distinct variables, k1 and k2. It's very important that you don't use the same variable for both because they might take on different values. For example, we can see this if we take p to be 5 and q to be negative 3. We also ask ourselves, what does it mean for a number to be even? A number is even when we can write it of the form 2k, where k is an integer. Looking back to the original problem, we see that if p and q are odd numbers, then p plus q has to be of the form 2k1 plus 1 plus 2k2 plus 1. And after some algebra, we get the result at the bottom. Now k1, k2, and 1 are all integers, so when we add them up, we get an integer. Thus, since we can write p plus q of the form 2 times an integer, this means that p plus q has to be even. At this point, we would be ready to do the formal write-up. However, I will not be showing the formal write-up for any of these problems for the sake of time. Hopefully you guys can figure out from here. Now on to problem 2. If p squared is even, then we need to show that p is even. A really common mistake is to try to solve the problem like this, where you plug in 2k for p, and then you do some algebra to show that p squared is even. What you've proven here isn't the original statement, but a different one entirely. You've shown that if p is even, then p squared is even, which is the converse of the original problem. Another common mistake is to try to blindly brute force problems like these with algebra. The problem with just algebra alone is that we end up in situations where we get stuck and don't know how to proceed. The key to solving this problem is the fact that every integer is either even or odd. If p is even, then that's great. That's exactly what we want to show. So then if p is odd, we have to show that this leads to some kind of contradiction, so that it's impossible for p to be odd. Alright, so suppose that p is odd, and we can write it of the form 2k plus 1, for some integer k. Will p squared be even or odd? Let's find out. And after some algebra, we get this expression here. Integers times integers are integers, and integers plus integers are integers. So 2k squared plus 2k must be an integer. So then we see that if p is odd, then p squared has to be odd, but this contradicts the condition that p squared has to be even. Thus, p can't be odd, so it has to be even. Now on to the last problem for today. We need to show that the square root of 2 is irrational. A number being irrational means that it's not rational. A number being rational means that it can be written as a fraction of integers. Or to be more specific, we mean that we can write a rational number of the form p divided by q, where p and q are integers. So a number being irrational means that it can't be written as a fraction of integers. Also, notice that all integers are rational. This is because you could take any integer and write it as itself over 1. To show that the square root of 2 is irrational, we have to show that we get a contradiction if we write the square root of 2 as a fraction of integers. So suppose for the sake of contradiction that we could write the square root of 2 as a fraction of integers, p and q. Then after some algebra, we see that we must have 2q squared equals p squared. And now, notice that if we divide the left side by 2, we're left with an integer q squared. But since the left side equals the right side, if we divide the right side by 2, then we must also be left with an integer. But then this means that p squared is even. And from the previous problem, we know that if p squared is even, then that means that p has to be even. That's right, sometimes problems we do earlier can come back to help us solve harder problems. Anyways, since p is even, then this means that we can write q squared as 2 times an integer k1 squared. But then using the same logic as before, we know that q also has to be even. Things are getting a bit cluttered, so let's make some space. So to summarize what we've shown so far, if it is possible to write the square root of 2 as the fraction of integers p and q, then p and q both have to be even. But this means we can cancel out a 2 from the numerator and the denominator, so we're left with a fraction of some integers k1 over k2. This is a major problem because there's nothing stopping us from repeating this process. Using the same logic as before, we know that k1 and k2 both have to be even, so we can again pull out a factor of 2. But we can do this infinitely, which is only possible if p and q both have infinitely many factors of 2, which is impossible. So the square root of 2 can't be rational, therefore it is irrational. In the write-up for this problem, it may be a bit awkward to talk about the process of pulling out infinitely many 2's in a formal way. Thankfully, there's a trick to get around this that will also shorten the amount of work you have to show. The basis of our argument was to show that writing the square root of 2 as a fraction of integers leads to a contradiction. The trick to shorten our work is to make another assumption, that the fraction p over q is fully reduced, meaning that they have no common factors. Then, the first time we pull a 2 out of both p and q, we can immediately stop, because this contradicts our assumption that p and q have no common factors. You're probably wondering right now why we're allowed to make this assumption. I mean, don't we have to consider the case that p over q isn't fully reduced? It turns out we don't actually have to worry about that case, because if the square root of 2 could be written as a non-reduced fraction, then we can just reduce it. So we can assume the fraction is fully reduced to begin with without any problems. By the way, this trick of making assumptions without reducing the scope of what we can prove is called without loss of generality. Anyways, thank you all for watching. If you want to see more videos like this one, please like and subscribe. In the future, I plan on making a lot of videos that tackle different subjects in pure and applied math, and maybe other science areas as well. So all the support this channel gets makes a huge difference. Also, leave a comment if you have a video idea you want to see in the future. Thanks again for watching. Bye-bye.